Okay, welcome everyone to the last lecture. So thanks for taking this journey with me so far. And we have only this more lecture to go. And obviously, I would like to tell you more about knots because I like them very much, and I think they're pretty cool. But we haven't really seen any really good methods to study them yet. So knot theory takes a while to get started. But I would like to tell you at least about one more invariant of knots, which is very computable, quite strong, very beautiful, so geometrically very appealing, topologically very appealing, and it relates to surfaces, which we have seen before. So last time I finished with a kind of combinatorial coloring of knots, which is essentially just a combinatorial datum, and today I'm more up for a geometric or topological datum. And the notion I'm going to explain throughout the whole lecture is what is called a Seifert surface, named after a person named Seifert. So from the 20s or 30s of the last century, when knot theory really gets started. And it's actually a very simple definition. So it's an orientable surface that has our little knot K here as its boundary. So the keywords are orientable surface. We kind of know what that means. So no projective planes, no Mobius strips or anything. And the second is it has a knot as its boundary. So this will imply in the language we are used to that, this may be a bit too much here. Give me a second. Now come on. Yeah, that's maybe a bit better. And this will imply in our usual language that P is 0 for the surface and D is 1 because it has exactly one boundary component given by the knot. Remember, the boundary is just a cycle, and now the cycle just arranges itself a little bit crazily, namely just following the knot around. Okay, so that's the definition of a Seifert surface. And the whole theory, not sure what's going on here. Okay, whatever. The whole theory lives through examples, so I'm going to show you several examples. After I state the not quite trivial theorem, I'm going to prove it, and it's very nice. It has a combinatorial and a real-world proof, and I'm going to show you two proofs. The combinatorial one, so the mass one if you want, and the real-world one. So because those Seifert surfaces actually exist in the real world. So it's kind of very exciting. So surfaces in general, as long as they are orientable, they should exist somewhere in our real world, and these ones actually appear. But just from the outset, it's maybe not super obvious that this is actually true, but we have those knots, those Seifert surfaces associated to knots, and they will play the key role in defining really a geometric invariant associated to a knot. We'll see what that means. It's really beautiful. So we will see what it is. But in general, note that it's a Seifert surface, not the Seifert surface. So it's associated, you will see it, to a diagram. So it's not unique. There are many, and we are kind of looking for the easiest one, the minimal Seifert surface, if you want. We'll be more precise in a second. I'll prove this result by showing an algorithm or actually a real-world construction for any knot. And the algorithm is kind of what you then run in practice. It's really simple. You'll see what it is. It's actually a really powerful idea. But let me show you some of these surfaces before. So I have some video here. So the surface will be the two-dimensional area that is filled in here, and the knot is, well, the string you see at the outside, and maybe you can already see it. The surface has the knot as its boundary. So let's just run a few examples. So the knot here, that's the figure 8 knot, and whatever is filled in is the surface. And they look quite beautiful, actually. So here's another one. We haven't seen this example, but it doesn't matter. It's some form of a knot, and the surface kind of filled in. So another one. Always kind of the same idea. You have a knot somewhere, and the surface that bounds that knot. I hope you can see that the surface has exactly the knot as its boundary. So it kind of wraps around following the knot in some kind of crazy way. So here you go. Next one, kind of very beautiful object. I have something like 14 seconds more to go, so maybe one more. And here you go. Last one. So always note here, whatever the 3-twist knot is, it's the knot you see at the boundary, and the surface, as you can see in this picture here, the surface is exactly, has a boundary is the knot. So kind of weird. So they look kind of a little bit strange. They're very beautiful, but a bit strange. So we kind of need to prove why does it actually make sense for any knot instead of just, well, we want to prove the theorem. And it turns out that these beads actually show up in the real world. And if I would be a really good lecturer, then I would have prepared now some physical experiment, but instead I have a video for you. So actually they show up. So the real world proof is you just build the knot out of wire, put it into soap, and the film that is built by the soap is actually the Seifert surface. So we'll see a picture in a second. And physically what happens here is that the soap is very fragile, of course, so it tries to minimize its area, to minimize the tension, and it turns out that the minimal area surface that bounds the knot is exactly those funny Seifert surfaces. And because it's real world, they're always orientable. So real world never forms anything non-orientable, because that secretly we have learned that would live in 4 space. So a 3-dimensional picture will always be, well, a 3-dimensional picture will always be orientable. So let me show you, instead of doing it live, let me show you the video. So it's really, those things come up in the real world. So we'll see that picture with half twists in a second in the mass construction, but they usually look as follows. So for the trefoil knot, the trefoil knot is on the outside, the surface is on the inside. And it's exactly what is formed if you use a wired trefoil. This will be, yeah, there you go. So you need to get rid of a little bit of fluctuations, because it kind of tends to stick together, but in the end you get this beautiful Seifert surface, which is a bit fragile, and you can do the same for all the other knots as well. So we'll see in a second that for the figure 8 it will look like this. And the soap is exactly doing the same, which is extremely impressive. So here's a beautiful picture. So the soap film is the Seifert surface. As before, there will be some fluctuations because it's real world, but essentially what is formed is this beautiful type of object, which is the Seifert surface. Okay. So that's the real world proof that these things exist. Kind of very, very nice. So again, everything here is essentially very applicable. Even kind of a little bit of funny notions, they appear in real life. And you can really do this at home. Just build a simple trefoil or something. It really looks very amazing. You need a little bit of soap to do it. Okay, let me do the mass version for you. And this is exactly what you will run if you want to compute it. Obviously, if you're sitting there and doing the exam, maybe using soap film is not the most efficient way of doing it. So here's a very efficient way of doing it. So we just pick an orientation, and that just means we fix a way to travel around the knot. Okay, so we fix some way, and it doesn't matter, just fix some way to travel around the knot. So now every crossing will have some orientation on it, and we use that to create these little Seifert circles that we will see in a second, or that you already have seen actually in the pictures. I will come back to that in a second, by just doing the following trick. So if you think about the crossing goes like, in this example, goes like this, has 2 orientations. There's one way to get rid of the crossings, which is a very brute force operation, but there's essentially one way, by just splitting it in 2 arcs, one going like this and one going like this. And you never touch anything on the outside. That's why there's only one way, so you want to continue the orientations. And you just do that along the knot. And because you now got rid of all the crossings, what are left is a bunch of circles. We'll see a lot of examples in a second. And the circles that you see, this disjoint union of circles, these are the Seifert circles that you see everywhere. So, and if you do the Seifert circles, what you do, you just think of them as little platforms. The platforms are now really just surfaces. The surface obviously is a platform, so it bounds the Seifert circle, and you just connect them with a little twist along, well, the original connections along the crossings. I'll show you in a picture in a second. But that's essentially it. And by construction, you actually get an orientable surface which has a knot as its boundary, because everywhere else where we had no crossings, these are just disk-like objects, and you just put in disks, the little platforms, the Seifert platforms, and to connect them, you do those little twists, and the twists will ensure that it's actually orientable. So if you don't do twists, they will end up with a non-orientable surface. And the nature actually does those twists as well. It's kind of a fun thing. So here in my little example, so here I have 4 crossings. I look at the orientation, so let me do it here. So this one goes like this, right? So it's a little crossing. So I resolve the upper crossing like this. The next crossing is also resolved like this. The second crossing, this crossing goes like this, and this crossing goes like this as well. And if you get rid of everything, so these are the local crossings, and there will be a knot somewhere in the rest of the picture, which you haven't touched, and you will see these little Seifert circles that I call the little platforms. And so you should think of them as now filling them up with a disk. That's exactly one way what you can do. You can fill these in with a disk. Here's a disk. That's why I call them platforms. Here's a light green disk, and here's an orange disk. So we have 3 kind of floating disks, a dark green one, a light green one, and an orange one, and you connect them via those little twist type objects. And then they are one surface. So you connect them like this, and you do this because now the green one that stares at you hits the bottom of the dark green one, which makes it then orientable. You do the same here, you do the same here, you do the same here, and you end up with pictures like this, where these are the Seifert platforms that you form from the knots, and these guys are the twists. And the twists always ensure that the top of one platform ends at the bottom of the other platform, which makes the whole surface eventually orientable. It's a very simple algorithm, so you just need to do it twice yourself. You just take the knots, you get rid of the crossings, you end up with circles, and you glue in those little disk type objects. Okay, let's have a look again at this one, which is a figure 8. So it ends up being this picture. If you think of it, this picture, if you just put the 3 platforms underneath one another, you end up exactly with the picture in the video. And you can do that for any projection, no matter how complicated it is. Just fix a way to read around the knot, connect accordingly, and you get platforms and twists connecting the platforms. And you get those really beautiful pictures that are formed by the soap bubbles. So try to remember this one. I pull up the soap bubble again, and it looks exactly the same. So the trefoil soap bubble somewhere here. So that's the picture I had on the slide. And now let's have a look at the soap bubble again. It's exactly the same picture. It's really, really pretty amazing. So if you look carefully, so again, it gets rid of fluctuations. If you look carefully, you see actually, you see actually here that the soap kind of twists itself doing those little twists. Very, very exciting. I call this a platform construction. So Seifert's platform construction. Very, very beautiful. So let me give you some examples, some more examples. This one is cool. So here's a very easy one. So it's just one platform. There's just one cycle. You just fill in one platform, and there you go. And the Seifert surface is just this in this case. So the unknot should be easy, and the Seifert surface for the unknot is easy. It's a disk. And kind of the complexity of the Seifert surface goes along with the complexity of a knot. And the more complex the knot, the more complex the Seifert surface. And on the other end, and that's the whole point, the more complex the Seifert surface, then the more complex the knot as well. So if you compute Seifert surfaces, you learn a lot about the knot. And if it turns out to be trivial, then the knot turns out to be trivial. I'll make a formal statement in a second. So here, again, some pictures of those, some more pictures of those beasts. one from the top, or kind of whatever top kind of perspective. And you can, in this picture here, you can really see the little twists. So this looks at the surface from the top, and here the surface from the side, and you can really see the twists, which ensures that the bottom is different from the top of this little surface, which makes it two-sided, which makes it orientable and not a Möbius. And if you would again build this out of wire and use soap, you get really one of those beautiful little pictures here. For the various crossings, the numberation for the knots here is in the knot table. So figure 8 is the only knot with 4 crossings, so it's 4 crossings, knot number 1, 6 crossings, knot number 1, 7 crossings, knot number 1, 8 crossings, knot number 5. So it doesn't really matter what they are, but in principle you can just run through the whole list of knots and you get all of these little beautiful surfaces. It's a very, very cute idea. And it's very, very powerful. That's what I'm going to do in the remaining part of the lecture. And in the end, whenever you see a knot, oh, my mic crushed, I guess. Let me try to go closer to this one. So whenever you see a knot, then just compute its genus, which is an invariant we associate to the Seifert surface that I'm going to explain right now. So the mic's out of battery, apparently. Sorry for that. Let's just go ahead. Okay, so we have a Seifert surface associated to a knot, and it's orientable, so it has one boundary cycle, right? So we know, I said again, this implies P is 0 in our classification, and it has one boundary cycle, it implies D is 1. So there's only one open information, namely actually what is T, right? The number of handles in the surface, and that's exactly what we want to do. So the surface, by our classification theorem, I hope you recognize this by now, is actually isomorphic to, homeomorphic to a disk that's the boundary circle and a certain number of tori, a certain number of handles. And if you just do the calculation from the Euler characteristic, you can actually say, remember that the Euler characteristic is 2 minus d minus p minus 2t. Well, this is already 1, this is 0. You just solve for t, and you get this expression here in the Euler characteristic. So 1 minus the Euler characteristic of 2, some number bigger than 0. And we define the genus of the knot essentially, so those two numbers here are the same, as the minimum over all numbers that show up do it for a projection. Remember, you always do something for a projection and take the minimum over all of them. And that's called the genus of a knot. Don't ask me where the notion genus comes from. That's kind of classical, historical, but it essentially just means the number of handles in the surface. So let me just pull up the pictures again, because this is really impressive. So one of these guys, oopala, that's what I wanted to do. One of these guys here is actually secretly some torus with some boundary component, and you simply can't see that easily because it's kind of wrapped around in 3 space that you can't see it easily, but we can still use this one. Has some genus. I'll tell you in a second what it is, the genus actually is. And you can't see it because it's kind of complicatedly wrapped up in 3 space following the knot. But we can just use the classification, the powerful classification, to say that there is a genus associated to it, and we just want to compute it for a knot. And this is a really, really powerful invariant. I just say that again. So this is extremely good. So for almost all questions, well, at least that you will see in this lecture, calculating the genus will tell you what the knot is, essentially, or at least that it's not trivial. I will do a statement in a second. Okay, and here's an example. And I call this an example with proof because I want you to look at it carefully and follow me. So if our knot is the unknot, then we already know how to construct one Seifert surface for it. Here we go. It's just this one. Not very hard. It's a disk. And that's clearly a disk. So T is 0. Very good. And there might be 1 million different Seifert surfaces depending on the diagram. But since the genus is already 0, and we take the minimum over all of them, and it can't get lower than 0, it can't get smaller than 0, and we already found something of genus 0, the genus of the unknot is 0. Which in this case means just checking one diagram is sufficient because you already end up with a minimal possible number anyway. So I call this an example with proof, and I hope that was reasonably clear. So the point is that the genus is a really great invariant. It's extremely strong. It takes into account the whole geometry of this funny surface, which is really non-trivial, but it's also hard to compute in general because it has this minimum involved, and that just means you essentially need to know it for all diagrams, for all projections, which is very hard in general. But here, of course, it can't get lower than 0, and you already found one that is 0. So the genus of the unknot is actually 0 because it bounds a disk and it can't get easier. So and the fact that I'm quoting here, which is not completely trivial to show, it's not super hard, but certainly beyond the scope of the lecture, but you're free to use it, is how ridiculously strong the notion of a genus is. So the genus is trivial if and only if the knot is the unknot. So this is a foolproof way to check whether a knot is the unknot. If the genus is not 0, it's not. If the genus is 0, it is. It's a really, really strong invariant. And it takes into account the whole geometry of the setup of those little foam-type surface objects. A really beautiful result, as I can't prove. I just state as a fact. But again, anything stated here as a fact that you can definitely use if I would ever ask. But already for something like a trefoil, it's not very clear how to compute those, the number. First, we run into two problems. First of all, so what is actually the number of handles of this beast here? It's not so easy to eyeball, I guess. And second, we would need to argue that whatever it is, it will spit out 1, I can already tell you. So here's a handle in this picture that you can't see, it's very hidden. But we also need to make sure that it doesn't get lower because we need to kind of argue over all diagrams. So it's not very clear how to compute them. And I show you a really great method to do it, which is an extremely great statement. Okay, so from this outset, we have this extremely strong statement that the genus is trivial, if and only if the knot is trivial. And to kind of show at least one part of it is not so hard, that's what I did. And we kind of want now, I mean, this is fantastic. This is, for example, wrong for the coloring, right? The figure 8 knot had no 3 coloring, no interesting 3 coloring, but still it wasn't trivial. But here it is an if and only if statement. So it takes into account the whole geometry here, which is pretty good. So what we really need at this point is a way to compute the genus of a knot, which is a final kind of computation I will show you in this lecture. It's great. It's really, really simple. And essentially, we already know everything. You can already see it. You essentially only need to know the Euler characteristic. And we know 1,012 ways to compute the Euler characteristic. And we use one of them. So here's another application of the Euler characteristic. Remember, we started in the first lecture already, well, in the first week of lectures already, with the Euler characteristic. And it's kind of, it reappears everywhere, even here for knots, in disguise of the Euler characteristic of an associated foam, soap foam surface. And here it is. So it is very simple to compute, and I will do it in a second for you on the example I already had. So you just compute the platform picture. It has S circles. It had the knot had C crossings before, and that's the Euler characteristic already. So this is minus the Euler characteristic in this picture. So here minus chi, and here chi equals S minus number of crossings, which is really, really simple. To compute. Let's go back to the example just to do this for the figure 8 knot. The one I had here. So that's a figure 8 knot. Well, it has C equals 4. I mean, you just eyeball the number of crossings here. Obviously, there are 4. You just need to eyeball the number of circles. There are obviously 3. It's not really hard. So S equals 3, number of Seifert platforms. So chi is actually, chi of the surface is actually -1. So it's equals to -1, which is 3 minus 4. So the Euler characteristic of the surface, which is really not trivial at all, let me pull up the surface again. It's really not so easy to see if you just look at it. It's this one here. Do I have, yeah, exactly. So this one actually has Euler characteristic -1. So 1 is from the boundary cycle, and there's one handle inside. That's why it gets to -1. And again, it's not easy to see, but it's really easy to compute. Just counting circles and crossings. It's really, really simple. Okay, so note that this implies that t is 1 minus -1 over 2. So 1 minus -1 over 2 is 1. So actually, the genus of, so the number of handles of the picture, the phone picture, I showed you by now like 5 times, sorry for being repetitive, is actually 1. And again, I think this is pretty cool, because you really can't see the handle in the picture, which again shows you how powerful actually this approach of the main theorem is. Right? So sometimes the notions we are looking for are very hidden in kind of the way the surface sits in space. Okay, let's go back to this one. I skipped the proof, it's not very hard. Let me just do, I already did this example for you, I'll have a second example at the bottom, at the top. So the genus, we strictly speaking only get an inequality here. I will show you a stronger statement in a second. So we strictly speaking get that the genus of the diagram is 1. So the Seifert surface for the diagram, which, because we take the minimum over all, does not necessarily imply that the genus of the knot is 1, but it is in this case. And here's again another construction, a little bit more complicated knot. You resolve all crossings, you get those little platform type pictures. So here's the Seifert surface. We have those little disks and the twists glued along the Seifert platforms, and we just count. Again, it's really just a counting problem. So 1, 2, 3, 4, 5, 6 crossings, and I see 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 Seifert surfaces. Seifert platforms. So again, the genus here is at most 1. Turns out that it is actually 1. So it's really simple. I mean, the pictures are also not so hard to draw. You just draw those little platforms and the twists, and somehow the genus is kind of hidden in the way the surface twists itself. But we can use the main theorem to actually check that, which I think is pretty good. And in the end, it's a simple counting of crossings and circles that you see. Very powerful way. Just do that for a knot. It takes you 2 minutes to do it, and you get essentially the genus of the knot. And remember that the genus is ridiculously powerful invariant. In general, it can actually happen that this is strictly smaller because it depends on the diagram. But let me show you the statement that you can actually use. So if you have a non-trivial, and I won't do it, but if you have an alternating knot, and I will scroll back in a second to remind you what that means, then it's actually spot on. Just take an alternating diagram, do the Seifert algorithm with the platforms, count the number of crossings, count the number of cycles, and you get the genus, which is a ridiculously strong invariant, and really simple to compute. So there's an algorithm that does it, and it's essentially a counting problem on the diagram. So alternating, so this is an alternating diagram. It just means if you travel along the knot here, it goes under, so under, over, under, over, under, over, under, and so on. So you travel along, and it always alternates between you pass underneath and you go overneath, like you're taking a bridge, and you always go over and under and over and under. And as soon as you see such a diagram, what you should do is calculate its genus, because it's easy and it's powerful, and it essentially is enough to, well, it is enough to distinguish your knot from the unknot because of this little fact here. So as soon as the number you get out is not 0, you're good, and you just have proven that the knot is not the unknot. And it just takes, it just gets
works for so many knots, it's fantastic. It's an absolutely fantastic construction. Okay, so here's it again. The second one is also alternating, so under, over. Let me just get rid of my little drawings here, then it's a little bit easier to see. So it goes under, over, and so on. So again, we really get in this picture that the genus is on the nose one by just counting. And how great is that? I mean, you get it topologically invariant by just a simple counting. It's absolutely great. And it's one of the strongest knot invariants we actually see in this lecture. The proof is really not so easy. But again, it's stated here at the theorem, so you're definitely supposed to use it. So the main, well, if I show you a knot diagram, the first thing you should check, is it alternating? If yes, you run this algorithm. That's usually a very good idea because this is just such a strong invariant. And it behaves nicely. Let me just state it a little bit more here. It behaves nicely with respect to the hash sum. Again, one direction is easy and one direction is hard. So that the genus is lower equal than the sum of the genuses. It's easy, just run the algorithm on the diagrams you get, but the reverse implication is actually hard, but it's known. I just can't do it in this lecture. A great invariant that works really, really well with all the operations we have seen so far. And, well, I have done it for you. Let me go back. I think I haven't done the trefoil. We do the trefoil now live. So it goes over, under, right? So just choose an orientation. Maybe I should choose an orientation in a different color. And as you can see, if you travel along the knot, it goes over, under, over, under, over, under. Alternating, what do we do to an alternating one? Well, we just run the algorithm. So let me just mark our crossings here. So it travels like this. So it travels further here, and now what you do is you just locally, so here, this one here, let me do it in purple, just gets resolved like this, following the orientations. So it goes like this. So you just resolve it like this. This one here gets resolved in this, gets resolved in the same way, following the orientations, and you can already see that the last one gets resolved in the same way. And the Seifert picture you get is a big platform on the outside and a small platform on the inside. And let me do it again. Oh, no, we had it in the other video, actually. Well, in this picture, they are both of the same size, but just shrink the top one a little bit, and it's exactly the same picture. So there are two disks and 3 crossings. So we just do the count now. Number of circles is obviously 2. Number of crossings is clearly 3. So the genus is 1. Right? It's 3 minus 2. The Euler characteristic is minus 1, so the genus is actually 1 as well. Which shows that the trefoil is not trivial. Here's another proof that the trefoil is not trivial. It's not 0, so it's 1. And so that checks the trefoil. And I already did the figure 8 for you. We can go back here. So here's the calculation for the figure 8. Again, on this slide, I still state small or equal because the theorem just appears on the next slide. But actually, because it's an alternating knot, so it's equal to 1. So they have both genus 1, which shows you that it's not a perfect invariant. We can't expect a perfect invariant. So we can't distinguish trefoils from figure 8 using the genus, but we can say that they're not trivial in a really simple way by just following an algorithm. So there's nothing complicated involved. Just draw the diagram, resolves the crossings, count the circles, and that's it. It's very, 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 very simple and exciting. So for example, what you can also do is you can show that some inequalities like that, right? Using this one here. So if these knots are not trivial, so you don't add 0 in every step, the genus gets bigger, so the knots are all different, which is, again, a very simple proof that you can have infinitely many different knots constructed from our little hash friend, the hash construction. So the Seifert surface is really, really powerful construction. So let me just do it once more. So this was already, so this is the main statement about Seifert surfaces. So if you happen to have an alternating knot projection, like the trefoil projection here, or the figure 8 knot, or whatever kind of knot this is, then you can just run the Seifert algorithm. You just run it, and you get the genus, which is really just given by you compute the Euler characteristic, and remember the Euler characteristic is just the number of cycles, Seifert circles minus the number of crosses. It's really, really simple. And the genus is exactly what is written here, which is, again, a non-trivial result. Let me stress that again. And because you kind of can't really see it. Come on. Can't really see it from the picture. So this is the genus 1 picture. There's a handle somewhere in this picture. This is just what we proved. Okay, let me repeat what we have seen, with the main statement actually being just the fact that I quote here. It's really non-trivial to prove, but it's crucial. So it really tells you that distinguishing the unknot is a problem of calculating the genus of a knot. Okay, let me come to the end. So let me wrap up to my last slide. Okay, so we are kind of out of time, but so knot theory is this really beautiful topic where you have, it kind of connects to everything in mathematics and also in the real world. I showed you several real world examples already. Today we had those soap films, and it really is great. It goes on and on and on. And the main difference between knot theory and the surfaces is that we had a full classification for surfaces, which is very powerful. We used it all the time, the DPT, and for knots that's just not happening. So for knots you need more and more invariance, and so this was one of my starting problems. There's a right-handed trefoil and there's a left-handed trefoil, and if you would build them out of rope, you could convince yourself that they are not the same. But if you would just go back and check all the invariants we have seen, so what have we seen? We have seen the crossing number. We have the same crossing number. You can just eyeball that, right? They have 3. We have seen coloring. They have the same coloring. Yeah? We have the same number of colorings. That's also very easy to see because kind of the picture is symmetric in itself. They have the same genus, which was the third invariant. So we can't distinguish them yet, which is actually very sad. So in a perfect world, I would have a little bit more time and could show you one of the new powerful ideas to distinguish this knot. So let me just tell you a bit about the history here, and then I'll tell you a little bit about what happens next week. So in the very early days of knot theory, Max Dehn gave a proof that those two knots are not the same, but it was a really complicated proof, and for about 80 years there was no other known proof. So there's no known invariant in classical knot theory that can distinguish those two knots, which is really a pity, because if you build it out of rope, it's actually really simple to see that they are not the same knots. And so roughly 30 years ago, in the 80s of the last century, Vaughan-Jones came up with an extremely powerful construction of a new knot invariant, which I can't show you anymore because I don't have any time, which can distinguish those and many, many more knots, and was awarded the highest prize in mathematics, the Fields Medal, for that discovery. It's a really, really simple idea again, and it's much more powerful than anything I've shown you, but we're out of time. That's just what it is. I'm just pulling it up to tell you it's not over here. It just goes on, and knot theory is one of the most active fields of modern research for various reasons, because it's applicable, it's beautiful, and it's also hard up to a certain degree. So that's just what it is. Okay, so the few takeaway pictures are we have seen 3 topics in this lecture. So the first topic is what I call graphs, which is anything about graphs, including mappings, because mappings are embedding of graphs. And all of these are very applicable. So the brain is a graph. I said that at the very beginning, and I actually found a nice picture. So people model the brain as a huge graph with many vertices and many edges, and kind of the graph theoretical structure of the brain, well, kind of plays a big role in how we perceive the world. And biologists or neuroscience, they really use properties or constructions from graph theory, like we have seen them, to study the brain, which I personally find is very great. So clearly one topic in the exam will be graphs. Yep. We have seen a second topic, which were surfaces, and there was really the main theorem about surfaces. So essentially, we know everything about surfaces, which is very different from this third topic. But we know everything about surfaces, and again, surfaces kind of show up everywhere. I showed you another example where surfaces showed up today as kind of those funny soap films that you can actually build at home. But the most prominent example maybe in the real world is that people kind of try to figure out what the shape of the universe is. So they try to figure out the geometry of the universe, and they use methods as we have seen it in the lecture to do that. And why is that a hard problem? Well, we can do the two-dimensional version for you. I'm standing here, and I just see a surface, but I can't really tell what it is. Of course, I know the surface of the Earth is a sphere, but just from my local picture here, I can't tell. Right? It just looks flat. And for the surface, for the Earth, we have different methods to do it. But for a huge beast like the universe, it's actually not so easy to tell what the shape of the universe is. And it turns out that it's probably not a sphere, by the way. And people use methods like we have seen them in this lecture to study the universe itself. So the brain and the universe, which I find really amazing. So clearly another topic in the exam will be surfaces. And we have seen the last topic, so what I just showed you up to this point, which were knots, kind of really beautiful embedded, this picture of embedded strings. And the main point of knot theory is that you can't classify them like surfaces, so you at least want to list them having as many invariants as possible. And the invariants we have seen were mostly the coloring and the genus from today. And I really recommend to compute the genus for everything that alternates, because it's such a powerful invariant. And again, this is not just abstract math, it's all very beautiful. I personally find it very beautiful. But it's not just abstract math, so the basic building blocks of life, DNA and proteins, they actually form knots, and most of their properties come from how they are knotted. And what people do in those areas is they compute something like the coloring or the genus or whatever of their proteins to kind of make sure they know what knot it is. Exactly what I will ask in the exams. I show you a knot, and you should decide what kind of knot it is, essentially. And what you do is you calculate all of the invariants. It's exactly what those people in this case, what is it, life biology or something, what they actually do. Okay, yeah, that's it. Thank you very much. I had a great time. I hope you enjoyed the ride.